If you've ever written any Go, you've written a function. I mean, it's the most basic building block of the entire language. But what's hiding under that simple surface? Well, there's a whole set of deliberate design choices that make Go what it is: simple, incredibly fast, and safe. So today we're going to peel back the layers of the humble Go function, starting with its basic syntax and going all the way to its role in powering Go's legendary concurrency. All right, let's jump in. Here's our game plan. We're going to start with the absolute basics, the anatomy of a function. Then we'll get into one of Go's coolest and most unique features, how it handles multiple return values and errors. After that, we'll check out some special features like defer and anonymous functions. Then we'll talk performance, how we pass data around. And finally, we'll see how functions become the absolute heart of Go's concurrency model. Okay, first things first. To really get what makes Go functions so special, we have to start with the syntax. And yeah, it looks simple, and that's the whole point. But trust me, every single piece is there for a very good reason. So for this whole breakdown, we're going to use this one function as our guide. It's a great example because it's what we call idiomatic Go, which is just a fancy way of saying it's the standard, recommended way of writing code. It's called squares of sum and diff. Pretty clear, right? It takes two 64-bit integers, a and b, and it returns two 64-bit integers, s and d. Let's pull it apart. Every single Go function has these 5 parts. First, you've got the func keyword. Easy enough. Then the name. Next up, the input parameters inside the parentheses. And notice something cool here. The type, int64, comes after the variable names. That's a Go thing. The fourth part is the return values, which are also typed. And this right here, this is one of Go's killer features, native support for multiple returns. Finally, you have the body inside the curly braces. That's where all the magic happens. So let's dig into that a little more. The ability to return multiple values isn't just a cool party trick. It is absolutely central to Go's entire philosophy on how to handle outcomes and especially how to handle errors. And this leads us to maybe the most common pattern you'll see in, well, pretty much any Go code base out there, a function that returns both a result and an error. You see, the creators of Go were tired of how messy error handling was in other languages. So instead of throwing some exception that totally messes up your program's flow, Go functions just return an error as a normal value. It's right there in your face. You can't ignore it. And this slide really gets to the heart of the philosophy difference, right? In a lot of other languages, you have exceptions. An error happens and boom, execution stops and jumps to some catch block way over there. But in Go, an error is just another value. It's nothing special. This was a very deliberate choice to force you, the developer, to confront errors immediately. By making you write that if error not equal to nil check, the code becomes way more linear and predictable. There are no hidden surprises. This all sounds really clean and simple, but how? How does a computer, which for decades has used a single register for a return value, actually pull this off? Is it some kind of compiler magic trick? Well, it's not magic, but it is pretty clever. The answer, as this Redditor explains, is all about the Go Application Binary Interface, or ABI. It's basically a set of rules for how compiled code talks to itself. Think of return values into those pockets first. If the values are too big or there aren't enough pockets, it just sets aside a little space on the stack, the function's main workspace, and puts them there. It's a really efficient system that uses the best tool for the job. Okay, so beyond the basics, Go gives its functions a couple of what I like to call superpowers that help you write safer, more flexible code. Let's look at 2 of the big ones, the defer keyword and anonymous functions. Oh man, defer is just so elegant. It solves a problem we've all run into, cleaning up our mess. You put defer in front of a function call, like deferFile.close, and you're telling Go, hey, I don't care how this function ends. If it works, if it fails, if it panics, I want you to run this cleanup code right before you leave. It's a guarantee you won't leak resources like file handles or forget to unlock something important. So what happens if you have more than one defer? Well, they get executed in last in, first out order, or LIFO. The easiest way to think about this is like stacking plates. The last plate you put on the stack is the first one you take off. So looking at the slide, the third defer you add is the first one to run when the function returns, then the second, and finally, the first one you wrote. It's perfect for nested cleanup tasks. Go also has anonymous functions, which are, exactly what they sound like, functions without a name. You can just define them right where you need them and even run them immediately. But the real magic happens when they become a closure. That's when the anonymous function remembers and can use variables from the world it was created in, even after the original function is gone. This is super handy for bundling up a little bit of logic and its state, especially in concurrent code.
All right, let's talk about speed, because how you get data into a function is just as important as how you get it out. And this is where understanding the difference between passing by value and passing by pointer is absolutely critical for performance.
So here's the one rule you have to burn into your brain. Go is always, 100% of the time, pass by value. That means you are always passing a copy of a variable to a function. The key and the thing that trips people up is understanding what is being copied. Is it a copy of the actual data or just a copy of the memory address that points to the data? And this slide just lays it all out perfectly. Imagine you've got this big 10 kilobyte struct. If you pass it by value, you are copying all 10 kilobytes of data onto the stack for that function call. That is expensive. But if you pass a pointer to that struct, what gets copied? Just the pointer itself, an 8-byte memory address. The performance difference is just massive. For big data structures, it's a no-brainer. You almost always want to pass a pointer. And this is where it all comes together. This is the top layer. In Go, functions aren't just for keeping your code tidy. They are the fundamental unit of work for Go's world-class concurrency. They are literally the things that run inside your Go routines. A classic example of this is the worker pool pattern. You see this mistake a lot with people new to Go. They just spin up a new Go routine for every single task. That's a bad idea. You can totally swamp your system that way. The worker pool is the solution. You create a fixed number of worker Go routines, and they just pull tasks from a shared queue. This gives you precise control over your concurrency. And the beautiful thing is, how do you build one? You guessed it, with functions and channels. You make a channel for jobs, you start a few worker Go routines, each running a worker function in a loop, and you just feed tasks into the channel. The function is the worker in the pool. It's such a simple, powerful pattern built right on top of the foundation of the Go function. So let's just pull all that together for a second. We've seen that the simple syntax of a Go function is totally intentional. We've seen how multiple return values completely change the game for error handling, making our code more robust. We've got superpowers like defer for safety. We know that passing data by pointer is key for performance. And at the very top, functions are the engines that drive Go's amazing concurrency. So I want to leave you with this final thought. When you see a language feature designed with such a clear philosophy, a philosophy that prioritizes simplicity, being explicit, and high performance, it doesn't just change how you write code, it actually changes how you think about building software. So the question is, how does this approach to function design change the way you'll solve your next problem?